Hello, everybody, and welcome to Alex Derives Stuff. Today's derivation here is a challenge. I have been challenged by the internet to do an integral. Which integral, you might ask? Well, this integral, which if you're at all familiar with integrals, practically if you know what an integral is, you probably know how to do this one, right? You just get a cubed over 3, right? Of course, the reason you know how to do that is because you memorize this particular rule. Like it's the first integral rule you probably memorize is the power rule, is how to integrate a polynomial, basically, right? So here's what the challenge was, is to be able to do this integral without the well-known power rule for antiderivatives. And I'm going to go a step further and assume we don't know any antiderivatives for any functions except for a constant. So here's what we're going to use for this proof. Substitution. So we were going to use a heaping helping of substitution to like change this into an integral that is easy to do. And then we're going to use this fact that if you integrate the function 1 from 0 to some number a, then you just get a, right? It's a rectangle with a height of 1 and a base of a has a area of a. All right, so how's this going to work? Well, first I'm going to magically do a substitution. So here's the substitution: u equals 2x minus a. Now, why am I going to do this substitution? We'll see. Well, all right, so if we rearrange it a little bit, so if we solve for x, we get x equals u plus a over 2. And so then dx is going to be a half of du. And then now here is the real reason I'm making this substitution. My new limits of integration will be from minus a to a. That's the big deal there. Okay, we'll see why this is a big deal. Basically, this is what is called a symmetric interval, and we'll be able to take advantage of parts of the function that is even and parts of the function that are odd. So when we plug all of this stuff in, we'll then get, and here's the reason we get this, by the way, right? Like, as we basically just say, well, if x is equal to 0, then, well, u would be equal to 0 minus a. And then if x is equal to a, then u would be 2a minus a, which is a. So the x equals 0 becomes u equals negative a, and the x equals a becomes u equals a. Okay, so if we plug in all of this stuff into that integral, what do we get? This thing, right? Like the x became the u plus a over 2, so that's x squared. The dx became the 1/2 du over here, and then the new limits of integration are minus a to a. With a little bit of algebra, we can clean this up a little bit. We could pull out a 1/8, right? Because so the 2 on the bottom here, that becomes a 4 when you square it, and then we got another 1/2 out here. So we can completely just pull out a 1/8. All right, and so for the time being, we're going to do a little cleaning up here. So, all right, if I expand the u plus a squared, that's all of this stuff in the integrand here, u squared plus 2au plus a squared. Hopefully everybody knows that rule. I think it's probably reasonable to move the 8 over to the other side for now. Okay, let's get rid of the fractions. All right, so what now? So next trick, split up the integral. Now, I wouldn't have to do this if I already knew ahead of time the even and odd function tricks. So that if I had those listed ahead of time, I could do this a lot faster. So we're basically deriving those even and odd things from scratch. So we split up the integral, and we're going to split it up into 2 intervals from minus a to 0 and from 0 to a. So what does that look like? Well, all right, so yeah, minus a to 0, 0 to a, and it's the same stuff inside each one. Cool so far. So far we've shifted it. It seems like we're making our integral more complicated here. Now the left integral, we're going to flip the limit. So we're just going to do another substitution. W, if we do 2 u substitutions, I guess it's a double u substitution. And when we do that, the new limits will be from a to 0, right? Because if u equals negative a, then w would be equal to a, and if u equals 0, then w would be equal to 0. And the du will be replaced with a negative dw. So if we just do this with the left integral, here's what we get. So the u became a minus w squared, right? And then we got a minus w here, and we got a minus dw here. And yeah, okay. So let's clean this up a little bit, right? Like, so then minus w squared, well, we can get rid of that negative, and then this minus here, we can move it out front. For the moment, I'm going to leave this minus in front of the dw alone. Okay, simplifying. And then now here's fun trick is, so I've got my limits for this first integral from a to 0. And I've got this minus sign here. So if you flip the limits, we can make it go from 0 to a. Okay, so now 0 to a, the dw is now positive dw, right? And so now we've got this as this 8 times our original integral equals the sum of these two integrals where they have the same limits of integration. Okay, it'd be nice. All right, let's clean this up. We don't we could use any letter for our variable in the inside of the integral. So let's just change them all back to x. So if we do that, all right, same integrals as now x is the variable again. And what do we got? Oh, hey, we can combine these, right? We've got two definite integrals from 0 to a. We can add them up by linearity, I guess, right? So if we combine them into a single integral, we will see, oh gosh, there's so many things that simplify here, right? So for one thing, this minus 2ax cancels with this plus 2ax here. This x squared adds to this x squared, and then this a squared adds to this a squared right here. So if we simplify even more, 8 times x squared, 8 times our original integral is equal to the integral from 0 to a of 2x squared plus 2a squared dx. All right, I think we're getting somewhere here. Let's go even further. Let's factor a 2 out of the integral on the right. Okay, and then we can take this 2 and divide it over, and it'll become a 4. Okay, it's looking a little bit nicer now. Now we'll take this integral on the right here, we'll split it up into 2 integrals, right? Like, so now we got 4 times our original, our original integral just popped up again here. So 4 of our original integrals equals 1 of our original integrals plus whatever this thing is. Now, despite the way it may look here, this a squared, we're integrating a constant here for this rightmost integral. So what we could do here, well, I've got 4 of our original integrals equals 1 of our original integrals plus this thing. So we could subtract this dude over to the other side. Oh, and so now we've got 3 of our original integrals. And then we also took this a squared and we factored it out of this integral on the right. So it's a squared integral from 0 to a of 1 dx. All right, now here's the only integral we're going to have to do. This one. This one, remember, was a. So, oh, okay, so 3 times our original integral was a squared times a. Clean it up. 3 times our original integral is a cubed. Divide the 3 over. Our original integral was a cubed over 3. So we've just proven, using nothing really but shifting properties of the integral, and there's things that happen when you do substitution and linearity and stuff like that, and that we've shown that the integral from 0 to a of x squared dx is a cubed over 3. I guess we just proved the power rule. All right, so that was my solution to the integrate x squared challenge. I hope you guys enjoyed that. I hope that's different than any of the solutions that you've seen before on this. And it is an illustration of one of my favorite tricks for evaluating integral, particularly definite integrals, is you can take whatever your integral is and move it over to a symmetric interval by just shifting it or doing some kind of substitution. And then once you do that, you can split it up into even and odd parts. And so this notion of even and odd functions becomes a really handy trick for evaluating certain types of definite integrals. Okay, so maybe you can get something bigger out of this. Hopefully I will have more derivations for you soon.